Experiment 4, rates of chemical reactions, a clock reaction. Now, the objective of this experiment was to obtain a rate law, including rate constant and orders, and the activation energy for the reaction. Now, before we get into that, I'd like to go over some important equations. So first, we have the basic equilibrium equation, A plus B equilibrium C plus D. This is then manipulated to equal Kc equals the concentration of A times B divided by the concentration of C times D. This is used to find the rate. Now, that is then plugged in to the equation below. Rate equals K, A to the X, B to the Y. This is used to find the rate law all, meaning the 0th order, 1st order, or 2nd order. Then we have the Arrhenius equation. K equals the pre-exponential factor minus the activation energy divided by the ideal gas constant times the temperature. Now, some important things that I would like to go over before this experiment is what we're actually solving for. So when we're solving for the activation energy, we're solving for this curve right here, for what gets the reaction started, and then here the energy is being released and the reaction is taking place. So some background on what this experiment actually is. So 10 separate reactions using various initial concentrations of peroxide disulfide and iodine were conducted to determine the initial rate. The initial rate was then determined. Once the initial rate was determined, it was then possible to determine the rate order of the reaction. And then once the rate order was known, then the rate constant could be solved for. So this graph shows how the conditions affect reactions. So looking at experiment B, all the B's highlighted in yellow. Look at the temperatures is what we're specifically looking at, the temperatures versus the time. So first experiment number 2, B was taking place at 22 degrees Celsius. The time for the reaction to take place was 2 minutes and 4 seconds. Going down to reaction 8, B highlighted in yellow, the temperature was 37 degrees, so it was much hotter. The reaction only took 34 seconds. So this shows how the higher temperature of a reaction increases the speed of it. Now looking at number 10, also be highlighted in yellow, the reaction is 22 degrees just like it was in number 2, but the reaction only takes 5 seconds. This is when the catalyst was introduced. This gave another pathway for the reaction to take place and avoid having to breach that activation energy. Then, looking at the C's highlighted in blue, we have experiment number 3 at 22 degrees Celsius took 1 minute and 5 seconds. Then number 6, C, at 6 degrees Celsius, so much colder, took 4 minutes and 42 seconds. This shows how a lower temperatures increases the time for a reaction to take place. So here are just some basic example reactions, kind of finding basic values that are used later on to solve for the rate. So here we have an example reaction of A, solving for moles. So we have 0.00300 liters of peroxide disulfate, and this is transferred to moles by multiplying by 0.200 moles of peroxide disulfate divided by 1 liter to give us 0.00600 moles of peroxide disulfite. This was then used to find the molarity of peroxide disulfate. So we have the moles we just solved for divided by the total amount of liters in the reactions, and that gives us 0.0500 moles of peroxide disulfate. Then we have some more example reactions that will be used much later throughout the slideshow. So first we have the example equation of the consumption of the peroxide disulfate. So we're solving for the amount of peroxide disulfate that was consumed during the reaction. So this is used by the molar equation. So we have 1 mole of peroxide sulfate divided by 2 moles of peroxide sulfate found from the molar equation, or the balanced equation, I'm sorry, times 4e to the negative 5th, giving us 2e to the negative 5th moles of peroxide disulfate that was consumed. Now this is then solved to find the initial rate. And this was done many times for iodine as well as peroxide sulfate. These are just the example reactions. So the moles consumed was then plugged into this equation here. So we have the moles consumed at the top divided by the total liters of the reaction times multiplied by the time the reaction took, which giving us initial rate for peroxide disulfate of 2.11 times 10 to the negative 5th. Now, that was so important to find so that we can now find the rate law using this equation up here, rate equals K, A to the X, B to the Y. So right here, we're going to start out with finding iodine. So we found the initial rate, like the examples previously. So we found the initial rate for iodine, and then the initial rate for peroxide disulfate. So in this equation, we want to set it up to where it's 0.05 times 0.05 over 0.1 times 0.05. The iodines cancel, rendering the equation 0.05 divided by 0.1 equals the initial rates divided by each other. Now this then was plugged into this equation, solving for a of x. This gives us 0.5 to the x equals 0.5234. This is then manipulated to give us a to the x equals the natural log of 0.5234 from here, divided by the natural log of 0.5, giving a to the x equals 0.934, which is rounded to 1, so it would be a to the first power. This is then repeated for peroxydisulfate. So the peroxydisulfate cancels, rendering the equation 0.1 over 0.05. This is seen from here, 0.1 over 0.05, these cancel. Equals the initial rate, 2.11 times 10 to the negative fifth, divided by 1.34 times 10 to the negative fifth. Now this is then plugged into that equation up there, 2 to the y equals 1.574. It is then manipulated the same way the last way was. So b to the y equals the natural log of 1.574 divided by the natural log of 2, giving b to the y equals 0.654. Now this is very low, but in the sake of, for this experiment, we just rounded it to 1, so this would be b to the first power as well. So with this, we got the equation rate equals a to the first power, b to the first power. Now this renders a second order reaction by adding up this to the first power and this, giving us 2, rendering a second order overall rate law. This then unlocks the equation for us, natural log of k equals activation energy over r times 1 over temperature plus the natural log of a. With this, the pre-exponential factor was then able to be solved for by y equals mx plus b, which was rendered from the Arrhenius plot. Now, how does this apply? Well, what do rate laws actually do? So rate laws are what going to tell us the speed of the reaction, and then it also tells us what makes it slow up versus slow down. So here we have the different rate laws. So we had a second order rate law. So this is our rate law with a positive slope. This is a 0th order rate law with a negative slope, and then a first order rate law with a negative slope. So, as I mentioned earlier, we are using y equals mx plus b. This is rendered from our Arrhenius plot, from right here, our Arrhenius plot. M equals negative 8,074.3, b equals 22.072, and then our regression was 0.974. So now that we found this, we're going to solve for the activation energy. So, as I mentioned earlier, y equals mx plus b was manipulated to give the equation a equals be. So a equals e to the 22.072, meaning a equals 2.171 times 10 to the 10th mole of negative 1 s to negative 1. Then the activation energy was solved for through the equation EA equals mR. So the activation energy equals 8.314, the ideal gas constant, times 8,074.3 equals 6.71 e to the fourth. Now this answer is not in the proper form. The answer then was converted to kilojoules by dividing by 1,000. This gives us an activation energy of 6.71 kilojoules per mole. Now, why is this important? How does this apply? So, as I mentioned earlier, one of our bees had a catalyst. It took 5 seconds. This is represented here by the red line. It offers a shortcut. So we got an activation energy of 6.71 kilojoules per mole. So for the reaction to take place, it had to get to 6.71 kilojoules per mole, and that is at the point it reaches here, the activation energy. Now the reaction takes place, goes down, 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 and then we have the products from the reaction. But with the catalyst, you don't have to go up here like this. The catalyst offers a shortcut, which greatly increases the speed of the reaction, which is demonstrated by this line here. Catalyst, catalyst, and so instead of having to go here, we just have to go right through here, and then we're straight to the products. So you don't have to get as high of an activation energy due to the catalyst being there. So conclusion, what did we do? We were able to obtain a rate law, including the rate constant and the rate order, and then at the end, we also solved for the activation energy for the chemical reaction. We learned that a second order rate law is positive, as demonstrated from this graph right here. Second order rate law, positive. And then we also went over what a catalyst was. So a catalyst increases the rate of reaction by lowering the activation energy. So it doesn't have to reach that peak, it instead takes a shortcut and it increases the rate of a reaction.